Hello, my name is Rob Reynolds. Welcome to Business Calculus Chapter 2, Section 1. Today we're going to learn about the derivative and the slope of a graph. And you're going to learn that the derivative, which sometimes is denoted as f prime x, is equal to the tangent line, or the slope of the tangent line. So you've seen tangent lines before, and as the slope changes through here, here's the slope of 0, then the derivative is changing. So the derivative is actually defined as this, which I'm going to derive for you in just a moment. This is how to find the derivative using the limit process, and we're going to be exploring that in this section. So the first thing I need to let you know is the tangent at a point A, it is tangent. The function is in red. Here's the tangent line, but it's not tangent at point B. So tangent means that it only crosses the function at one point. And the way that business calculus students are going to recognize that they want you to find the derivative or the slope is they'll be talking about rates of change or the rise or the fall of a graph. So again, here's slope 0. Notice that that creates a max. That becomes an important part. And then this is kind of an interesting concept. Here, the function is increasing, but as the function increases, check out the slopes. It's very steep here, less steep, and even getting less, so the slopes are actually decreasing as the function is increasing. We'll talk more about that concept later. Again, secant line goes through twice, tangent line only once, and maybe you remember in your geometry classes where they talked about a circle and a line tangent to that circle. So again, another slide, it may be tangent here, but not tangent down here at point Q. And to find slope of a tangent line, we'll need to talk about rise and run. So delta y is going to be the rise value, the change in y, and delta x will be my run or my change in x. So delta is a Greek letter which we use for change. So to approximate the slope, not exactly, but I'll look at the rise and the run, and we'll say it's approximately at 0.11, the rise over run, the derivative, the slope of the tangent line is approximately 2 over 1. Now keep in mind, that's only at this 0.11. If I were to look at the 0.24, you can see it's much steeper, and I would have a different approximation. Again, you can go to Blackboard and download the handout, and you can kind of follow along with these examples. Let me derive for you the limit process. If this is my x of 2 and my y sub 2, my second point, this will be my x sub 1, y sub 1. I'm going to use the slope formula here. So slope is defined as what? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And I'll start right here. Y sub 2 is f of x plus h, and I'm going to let h be my change in x, minus this y value, f of x, all over x sub 2, which is x plus h, minus this x. And you can see this simplifies to something we were working with earlier, the difference quotient, but this becomes the basis of the limit process, or finding a derivative. If we take the limit and push delta x, which I'm letting be h, to 0, then we get the tangent line. What does that mean? Well, the distance between these 2 points is denoted as here. So if I were to put those 2 points even closer, you can see delta x is even smaller, and then even smaller. And so it's so small that that distance, the limit, goes to 0, and then it will only cross at 1 point. So again, it's kind of like taking that line and just moving it right back here, because the 2 points are just so close to each other you can't even distinguish between the first point and the second point, and then that would be the line tangent. Again, here's the secant line would cross twice, so that's just really your slope, y minus y over x minus x. But if I push that limit to 0, we get the tangent line. So we've got two definitions. There's how to find the slope of the secant, and there's some images of what secants looks like. But as these points get infinitely close together, and as x approaches 0, we'll get the tangent definition. So this is the one that we're probably going to be using the most, because this is another name for the slope of the tangent, the derivative. So we're going to use the limit process, which I just explained, But to find, we're not going to graph it and count rise over run. We're going to use this f of x plus h definition. So to use f of x plus h, it says go to the function, and every time you see an x, don't plug in x, actually plug in x plus h. Then subtract off the function, and sometimes I put parentheses around that, but this is just minus x squared all over h, and then don't forget to take the limit and push it to 0. That's your delta x. The change in x goes to 0. So let's multiply this out using my wife's square double square. So this comes out, remember you can't distribute this, so you have to 4 this out, but my wife has a rule, square double the product of x and h is x and h, just double it, plus h squared minus x squared all over h, and notice the x squareds cancel. Don't forget to evaluate the limit at the end, which oftentimes students do. Factor out an h so we can cancel the h. If I factor out an h from these two terms, I'll be left with 2x plus h. Don't forget to take the limit at the end, like many students do, so I'll just keep writing it. Finally, we'll evaluate, so 2x plus 0 is just 2x. Now this I like to call the tangent slope formula. Why? Because earlier I told you that the slope keeps changing as you move along the function. So this is a nice slope formula which will find the slope at any given x, and there's the x that we want to use. We want to let x equal -2. And when I throw in that -2 here, I get, of course, the slope to be -4. So what does that tell you? That tells you that at this particular point, the slope of the tangent line is -4. And again, here's how the author worked it out, but they get the same answer. I like using the h's because it's a little bit less confusing. Delta x looks cumbersome. So this one says find the slope of this graph. Well, let's try this limit process again. Every time, go to the f function, but don't plug in x, plug this in right here. So -2 times x plus h, instead of delta x, plus 4, minus the function. Again, I told you I like to put parentheses around that so we don't forget to distribute this negative sign. So the function is -2x plus 4, all divided by h, and don't forget, like some students do, to evaluate the limit by letting h be 0. So I'll distribute here, -2x minus 2h plus 4 plus 2x minus 4 all over h. Don't forget you're taking the limit. A lot cancels out here, and this -2h over h, you can actually cancel out the h's, and you're just left with -2. And by the way, the limit as h goes to 0 of -2 is just -2 because there's no h to even plug anything in. So you get a constant slope, which makes perfect sense because look at this. This was simply just a line, y equals mx plus b, and we know from the line the slope is -2. So that makes perfect sense. No matter what x value you choose, the slope will always be -2. So this one talks about that slope formula. So go find that slope formula again by using the limit process. Later we will learn another process, but for now you need to demonstrate that you can do this f of x plus h minus f of x all over h and evaluate the limit as h goes to 0. So this says go to the f function, which is right here, but don't plug in x. There's the f function, but don't plug in that x. Instead, replace x with this blue guy. This blue guy is always x plus h. Then don't forget to subtract off the function and evaluate the limit as h goes to 0 after you divide by h. Which oftentimes the goal is to multiply this out and factor out an 8 so you can cancel. Because we can't just do direct substitution because you can't divide by 0. So the function is really what? X squared plus 1. So I'm going to use my wife's square double square rule again. Square the first, twice the product, square the last. I have a plus 1 hanging around this time. But that's okay because it's going to cancel out with that minus 1. Divided by h and evaluate the limit as h goes to 0. So this time, these cancel. I can factor out an h, leaving me 2x plus h over h. And when I evaluate and let h be 0, I get, well, the same answer I had before, 2x. Then with that, once I find 2x, if the derivative is 2x, I can evaluate the derivative at -1, and say 2 times negative 1 is negative 2, and I can evaluate the derivative at positive 2 and get a 4. So there's maybe some answers, hopefully, that the author will get. Negative 2 and 4 is what I'm looking for. So let's see. So good, they got the same slope formula that we did. And there's the negative 2 and the 4. Again, these slides are posted on Blackboard, and you're welcome to look at those. Hopefully you're kind of following along with the handout that I've given you. So the derivative function, just did that problem. So to find the derivative using the limit process, it says every time you see an x, replace it with x plus h. So x plus h squared minus x plus h. Then subtract off the function. You may want to put that in parentheses. And the function is here in yellow, here in yellow, here in yellow. So I'm just going to subtract off 3x squared minus 2x, all divided by h. The limit as h goes to 0. So let's multiply this out. X squared plus 2xh plus h squared, and distribute the 3. 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 3x squared plus 2x. Hopefully I've done that right. This is a long problem. The limit as h goes to 0. Hopefully if you've done this correctly, some things will cancel. It looks like they do. Every term that's left looks like it has an h in it. So I'm going to take all 3 blue, factor out an h, 3h minus 2, cancel out the h, and then evaluate the limit of just what's left. Well, if I evaluate right there, that will go to 0, and I'm just left with 6x minus 2. So that is the derivative. And then you can evaluate the derivative at any point, and I don't think it told me to evaluate at any point, but I could. So let's see if the author gets the same thing. Yep, 6x minus 2. Sometimes there are some tricks to evaluate the limit process. Either you have to use the conjugate, or you have to find common denominators and add and simplify the fraction. Let's see what happens here. To find the derivative here, I'm going to use the limit process. So replace t with x plus h. So instead of 2 over t, I got 2 over minus the function. 2 over, well, really it's not x. It's really, I should probably just keep this at t, because I don't have an x in this problem, so it's t plus h all over 2, all divided by, what, h. So here's I probably don't want to use the conjugate, because I don't see square roots, and that's often, you know what conjugate is. When I have like 5 over 3 plus the square root of 2, sometimes you multiply by the conjugate, which changes that middle sign. So if you multiply the top and bottom by this, so when I see radicals, I oftentimes hit conjugate. But here I think I can just find common denominators. So the common denominator here is t plus h times the quantity t, and then I'll just divide by h. So instead of writing divided by h a bar, I'll do this sign. So if this is my common denominator, t plus h, then I need to multiply the bottom here by t and the top by t and bring down a 2t. And I need to multiply this guy by t plus h and t plus h. And don't forget to distribute the negative 2. And bring over a negative 2t minus 2h. Something should cancel. If they don't, you did something mathematically wrong. So I'm left with negative 2h over t plus h times 1 over h. Well, instead of dividing by h over 1, you can multiply with reciprocal. So these h's cancel. That should always happen, and I'm getting lazy. So remember, you've got the limit out here. Don't forget to evaluate as h goes to 0. So if h does go to 0, you've got negative 2 over t times t plus 0. And t times t plus 0 is just t squared. So there's the slope formula, and were we supposed to... They didn't give us a point, so I think we're done. Let's see if the author agrees, and there it is, the derivative. Sometimes dy, that's the same thing as f prime t. Sometimes the derivative of y with respect to t. Dy dx would be f prime x. So just notation for derivative. Lastly, we're going to talk about the difference between a function being continuous and differentiable. So sometimes when it's not continuous, then it's not differentiable. But sometimes it is continuous and it's still not differentiable. What does that mean? Here's a function that just continues right along, but check it out. What's the slope right here? It's a vertical line. It just is so and we know vertical lines have no slopes. So right at that point 0, 0, we say, nope, not differentiable. And of course, if it's not continuous, the slope from the left does not equal the slope from the right, so that's not differentiable either. And if it has a cusp, a sharp point like this, sometimes this absolute value function, graphs of v, has that sharp point, and again, it's not differentiable. Or a node, sometimes not differentiable. But they're continuous. So they're making a distinction. If it is differentiable, it better be continuous, but not necessarily vice versa. I hope this video was helpful.